absolute zero temperature is in the rest position, but with some energies, now the atoms is moved to new positions, something like this, right? So we're not going to have this. Instead, we're going to have this. So if you just erase everything, now at some specific time with a specific energies absorption of the system, the atoms is going to just like this. And then we want to express this as a wave with the wavelength lambda, something like this, right? We should have something. So we want to describe this as a wave instead of each atoms. Then we call this lattice wave. What is the difference between the lattice wave and the string? What is the difference between the string and the lattice wave? In lattice wave, only the atom exists. There is nothing between the atoms. Okay? And the tension exists in the string, but in a lattice wave, the coulombic force between the two atoms is going to react. Okay? So that is the difference. There is nothing in between the atoms in the lattice wave. In a string, the everywhere is going to be defined as a string itself, the density, mass, whatever. But in a lattice wave, we do not have anything in between the atoms. Okay? And we do not have a tension. Instead, we have a coulombic force in between. So naturally, in the lattice wave section, it's shown in the textbook, we want to see what's going to happen in some specific atoms with the nearest neighbors. Okay? So let's make it big of this section and then take this R alpha atoms, okay? And then A is a lattice constant, for example. So this is actually the A. So alpha atoms from some reference, and then the x-axis, the distance is going to be R times A, just simply like that. And then one atom before that, that is 1 minus A, R minus 1A, and the distance is R plus 1A for the atoms next to the reference. So all we have to do is just calculate the force up of this atom and force down, and then as we did for the string, we want to find the net force, which is up minus down, and then that is going to be related to the Newtonians. Newtonian is the F equal to ma, right? And then that is going to be m round t square round square psi, the displacement of this y-axis. So now the question is, how can you get this psi? How can you get this f up and f down? Okay. So as far as we can have f up and f down, then everything is simple. And following the notations which is given on the textbook, we have two angles corresponding to the, in the textbook, it is working on this, this atom and this atom and this atom, something like that. So this is the, in the textbook, this is RA, and this is R minus 1A, and this is R plus 1A, okay? And then the angles that has been shown here, this angle is going to be theta, and then this angle is going to be phi in the textbook, okay? So with using this trigonometry, we have the force R minus 1. This force means the force in between R minus 1th atom and in reference rth atom. So the force in between this, that is going to be called Fr, R minus 1. And naturally, the next one is R plus 1. Is going to be the force in between these two force. Okay, so this force and this force, you calculated this force and this force, and then use the trigonometry, then you can have F up and F down. Okay, that's what we are going to do. And this is the F, Coulombic force between the atoms, times cosine theta. And then this one is F sine phi. That's what the simple trigonometry. Okay? And then in the text, you have those force can be said psi r minus 1 minus psi r, and then it can be approximated to the F times A psi r minus psi r plus 1. So F net is going to be F net is going to be A over F psi r minus 1 minus 2 psi r plus psi r plus 1. Okay? Now, you just have the psi r minus 1 and psi r plus 1. And you know the solution of this psi going to look like A e to the I K RA. RA is the x, okay, minus omega t. This is nothing but the x. Okay, rth atom in the lateral distance A. And so r minus 1 is going to be A e to the I K r minus 1A minus omega t, and this is nothing but I e to the minus I K A times psi r itself. And with the same token, we can say psi r plus 1 is going to be A e to the I K r plus 1 A minus omega t then it's going to be e to the I K A now psi r. So everything psi r minus 1 and r plus 1 can be expressed in terms of this IR. And then you put this thing into this equation, then you can get the F net, right? In terms of the psi r. And then this F net should be related to the acceleration to get the wave equations. If you have any questions on this equations and mathematics, you can ask your younger brothers, which is in high school, okay? Then you end up with eta e to the minus ika minus 2 eta plus eta e to the ika equal to minus omega squared. And here the eta is going to be F over ma. The F is the Coulombic force between the atoms. And then ma is the mass of the atoms, and a is the lattice distance. So everything here is known, the constant values. We have some assumptions in this calculation, like we just think about the nearest neighbors. We do not count, take into account of the next nearest neighbors. We just think only the nearest neighbors. Something like that, okay? So we have some assumptions in there, but that is those assumptions are obvious, so you just go through it. Now, if you insert this, then omega squared is going to be now 2 eta 1 minus 1 half e to the ika plus e to the minus ika. Okay, and then you see this, the Euler theorem is going to be the sine, so that this should be 2 eta, 2 times sine square 2 over ka, something like this. And then that is 2 eta, 1 minus cosine ka. This is amazing. Okay, so when you look into this, then it can be converted to the sine, something like 4 eta sine square 2 over ka over 2. That is omega squared. And if you draw that, then you have some weird figures. Nothing like a straight line in the string. And remember, in a string case, omega versus k in a string. Let me remind you, omega versus k is going to be the straight line, and then the velocity is going to be tau over rho. That's what we have in a string case. Now, what happened to the lattice? If you draw that omega versus k in case of lattice wave, that is a sine curve. The sine curve is going to look like this, you know. And then here we do have omega maximum. In other words, in this lattice, it cannot have energies more than these energies corresponding to omega max. This energy is just nothing but the h bar omega. So if you set in this calculation, okay, in this analysis, we can see that in lattice atoms, it cannot have energies more than h bar omega max, according to that equation. That's very weird, isn't it? No matter how high energies you put into the system, the lattice, the atoms, the solids cannot have energies more than this. Then what happens if you put more energies to that solid? That's a very, that's not obvious. And then the next thing is the repeativity of the wave. Now, how come this is very much like this curve? When you increase the k, in other words, when you decrease the wave number, the energy is going to increase. It's not a straight line, but it's somewhere in the fashion, similar behavior. But what happens if you have more k values, higher values, then how come it's going down? It's going down again. And then how come it's going to go up and then repeat those things? And this is the pi over a, and this is the 2 pi over a, the k values. And here, this is the minus pi over a, and here, the minus 2 pi over a. That's very strange, isn't it? How can that happen? About the repetitions. Let me explain about the repetition first, because that's a most interesting point here. The repetition is nothing but a description, mathematical description of the atoms. Let's suppose, let me do some trick in here. Let me draw two let me see. Let's suppose we have an atomic displacement corresponding to this. Like one, let's put the 2 here, and the maximum, 2 here, and then 2 here, and then 2 here. So at some energies, let's suppose we can describe this energy state with some wave with k values. In other words, the k is, remember, is a 2 pi over lambda. So with this wavelength, we can describe this atomic movement, atomic status, say, with specific energies. But in this mathematics, we can say that this displacement can be expressed in other waves too. And that other wave, let's suppose we are going to use this wave to describe this, okay? And this blue wave, obviously, apparently, it has a different wavelength to the black line. But it can also describe the atomic status by observing excited status, by observing some energies from outside. So the repetition just means that we have a different value of k. We are going to express the same energy states, the same omega values. That's what it means. Okay? So we have a repetition so that when you draw this, you don't need anything more than this. Okay? You just draw this, and that is enough for the lattice wave descriptions. Okay, and then we call this brilliant zone edge. And that is enough for the description. And then next thing is, what is this omega max? All right. So what is the energy max, which is corresponding to h bar omega, okay? And that happens at the Brillouin zone. That happens at the Brillouin zone H. Okay. And then that the Brillouin zone is k equal to n plus minus n times pi over a. That happens. Okay, so this is the first Brillouin zone, and then the next one is the second Brillouin zone, things like that. So, what is the physical meaning of this? Why in a solid does not have does have the maximum energies? For k equal to pi over a, okay, omega max, it can really calculate it like 2 eta over the square root of eta, and then eta is as you have that f over ma, sorry, f over ma, okay? And this omega max is when you have h bar omega max, okay? Then that is the maximum energies, and then that can be, if you use the Boltzmann constant, if you divide the energy with the Boltzmann constants, or what you can get, the temperature, right? The Boltzmann constant is related to the energy conversion to the temperature. So we are going to have some kind of a temperature thing here, and then we call this Debye temperature. So Debye temperature means the temperature where the solid cannot have more than, okay, the maximum temperature. So that is going to be called, that is the lattice wave. All right? Let's see. So if you draw that, then this is the Debye temperature is related to the maximum values or Brillouin zone values of the K. Let's just think about the K when it is very small. In other words, if at this edge, it seems like it does have a straight line when the K is very small. And then let's see. What happens? Let's see what happens for small k. For small k, sine 2 over k